Okay, sorry about that little delay. So we're going to get into this final section of looking at the mathematical calculations behind using spherical mirrors. And I told you once before that there are two main real equations in mirrors and lenses. And it has to do with the two equations that are on the slide. Okay, so one of the things that we're going to be calculating is, based on the values that we know, right? We know DI is a potential option. We know that DO is a potential option. So the distance of the image created from the mirror and the distance of the object from the mirror. We know that we can figure out how high the image created will be. So how tall is the image and how tall is the object. We also know that we can create or figure out the magnification. The one that we haven't really talked about yet is that focal length. Okay, so we know that the focal point is halfway between the center of curvature and the vertex, and the length of the focal point to the vertex is known as the focal length. So I'm going to write that down here. Focal length. Now, here's where it gets interesting. I want you to look at the second equation on the slide and tell me if you notice something. Okay, this equation, first of all, you've seen before. We saw it using the camera obscura, right? So if we go to the pinhole camera, so you've seen this equation before. Have a look at the equation in green. And now have a look at this new equation or this new version of it. And something you're going to notice, I hope, is you're going to notice the addition of this minus sign. So to keep things straight, and I mean, I can explain the minus sign to you, but that is like an entire lecture in and of itself. But the rule is this, and it's fairly simple. When you are doing camera obscura, okay? Camera obscura, and this for whatever reason is being a jerk. So camera obscura, pinhole camera, you are going to use M is equal to HI over HO, which is equal to DI over DO. No minus sign. The reason we use the minus sign here is because something is interrupting that kind of the actual light ray from its actual source point at the topmost part or on the object to where it actually ends up, right? It gets reflected here. And we're going to see later that it's also going to get refracted. So with the pinhole camera, we see, if I go back here, that there's no interruption. And what I mean by that is that the light ray hits the pinhole and goes right through to the base of the screen, goes right through to the top of the screen. There's nothing, it's not bouncing off anything, okay? Here, the light ray is getting reflected. It's bouncing off the mirror. So when we look at these actual problems, we're going to include the minus sign. All right, so I'm going to write this one in blue. We're going to use this equation. So negative DI over DO is used for mirrors and lenses. Okay, not for camera obscura. So that's one way to keep it kind of going. All right, so the big thing here, the vast majority of the time, you are going to be asked to find things like you will be given some information and you will be asked to find things like image position, so the DI, the magnification, the height of the image created, right? So in order to do that, we're going to work through these problems. And you're going to see that it changes depending on where the object is in relation to the center of curvature and focal point of the actual mirror. So we're going to do this first one together, okay? We see that an object has a height of 4 centimeters and it's located 30 centimeters from a converging mirror, right? And we know that the radius of curvature is 10 centimeters. So given that, I want you to find the DI, the M, and the HI. And here's where it gets kind of interesting. We're going to end up using kind of a rearranging of things and a substitution here, okay? And actually, I don't even think we end up having to use a substitution, but it's going to end up being having a denominator that's a fraction. And this is where your kind of math rules are going to come into play. So first things first, I'm going to write my givens. I know that I have an HO of 4 centimeters. I know that I have a DO of 30 centimeters. And I know that my R is 10 centimeters, right? So given that, if I know what my R is, the radius, what is my focal length going to be? F is going to be R divided by 2, which means it's 5 centimeters. Okay? So now first things first, I am going to look at what's happening here in terms of, now I want to kind of just draw this out for you up here. I am telling you right here, okay, that we have this converging mirror, okay, and I'm telling you that an object is going to be, so I'm telling you that the center of curvature is here, so my radius of curvature there, and then this is going to be my F, and I'm telling you that the object, I'm just going to make this go on a little bit. I am telling you that the object is over here and it is 4 centimeters high. This is my object right here. Okay? Does that make sense? This is kind of a visual as to what's happening here. So number one, we want to calculate the image position. Where is the image going to be found here? Right? And later on, I'm going to do a little ray diagram here just to kind of prove to see what it is I found. And I'm going to see if this kind of matches up. I am going to use an arrow as my object, okay? Just so we know, an arrow pointing up. So first things first, I want to calculate DI. I want to know the distance of the image. Where is DI going to be here? So if I'm starting off with 1 over F, and this is going to be A, DI equals, je ne sais pas, that's going to equal 1 over DO, which I have, plus 1 over DI, which I don't. Through rearranging this equation, right, and solving for DI, we see that some fractions there get bumped onto the bottom. So a solo DI ends up being equal to 1 over our 1 over F here minus our 1 over DO here, right? And now I can input my values. I can actually input what's happening here. Okay? By doing that, I end up with 1 over 5 centimeters minus 1 over 30 centimeters. I can't do this if they're on, if they've got different sort of denominators here. So what I have to do is put them down onto the same denominator. So this ends up being 1 over, I will say 6 over 30, right, centimeters, minus 1 over 30 centimeters. Now math would have it that this ends up being 1 over 5 over 30 centimeters. And if I flip that up top, right, that ends up giving me here 30 divided by 5 centimeters, right? That should just be by 5, which is going to give me a DI of 6 centimeters. All right? So that's number 1. That's A. Now that I have DI and DO, now I can actually find my magnification. Now, remember that this formula, so I'm going to use a different color here for B. And I'm just going to move this down right here. Remember that M is going to be equal to negative DI over DO, right? Because it's also equal to HI over HO, but I don't have one of those. So now I'm just going to input my stuff here as negative 6 centimeters over 30 centimeters, right? What is 6 divided by 30? That's going to give us a negative 0.2. If this is negative and it's smaller than 1, what does that tell us? Both things are telling us something. If the magnification is negative, right? If it's negative, that's telling us right here that the image is inverted. It's going to be upside down. If the magnification is less than 1, it's telling us that it's going to be smaller, right? Remember that it's less, if M is less than 1, it's telling us that the image will be 5 times smaller, right? So if I want to kind of figure this out now, I know that my DI is going to be at about 6 centimeters. And if I gauge that R to be at 10 centimeters, well, 6 would have it right here and or so. And then I'm saying that it's inverted and it's going to be 5 times smaller, right? So I'm assuming that this little guy is going to be that big right there or so. Let's see later if I can draw this out, if my ray diagram proves this. Okay, we're going to try. Now the final thing here is looking for, and I realize I'm taking a lot of space, I'm sorry, we're looking for HI. Well, we just go back to our M. M is going to be equal to HI over HO, which means HI is going to be equal to M times HO, right? Does that make sense? So here, that's going to give us that negative 0.2 times 4 centimeters. HI is going to be negative 0.8 centimeters, right? That's the height of the image. Okay, does that make sense? So let me now draw my ray diagram to just see. First principal ray goes down, hits. Oh God, that's not what I wanted to do. Let's try that again. Okay, and then it goes through the focal point. Holy Moses. Love it when this works. Okay, let's try ray number 2. And we knew that wasn't going to work. It's too close together. Let's make this nice and big. Try it again. Yeah, that's not going to work. So I'm going to freehand this. Sorry, suckers. And then it's going to bounce off the mirror. Well, whatever. It's pretty darn close. It should actually be bouncing up here, but I'm not going to argue. And then we've got our third ray, which should actually just leave this guy and go right through. Oh, God. Not at all. Yeah, it's not going to work. But I think you can see that my ray would have worked. So roughly, the image is going to be in this area. And it actually does work, more or less. Had I measured all this out with actual centimeters and what have you, this would have been point on, bang on, perfect. Okay? So things to remember, DI is always a rearranged denominator fraction. The actual magnification will tell you things, right? If it's negative, you've got to remember what that means, that it's inverted. If it's a decimal, that means it's going to be smaller. It also, because for HI you get a negative number here, it also tells you that it's going to be inverted. I want you to give a try for the rest of these problems, and you're going to see that things are a little bit different, but the way to solve them is the same. Then what I want you to do is go back and look at this table. Okay, look at this table and see, are you actually really finding these things, right? Are they actually smaller, bigger, whatever? Are they inverted and upright? Okay, I want you to see if you're actually being able to prove that. So the calculation is the same for all three. You should have your textbooks at home. Your textbooks work through every one of these explanations. Okay, I will place answers down for the rest of them, but I will not necessarily do the work. So when I post this, I will actually place some answers in these guys, because this is telling you it's still 4 centimeters, but now it's changing the actual, it's changing the location. So what you're doing is you're starting beyond C to C, between C, and let me draw this. I think that'll make much more sense. So if you've got your principal axis here and you've got your curved mirror here, okay, so it's telling you, let's say C is here, F is here, that's not F, V is here. So number 1 that we just did had, so example 1 was back here. Example 2 is right at C. Example 3 is between C and F. Example 4, I don't think I give you one at F because it's not mathematically doable, but you also have another example where you've got the actual image here. Let me just see how many I give you. Yeah. right? So this guy here is right at C because the image is located at 10 centimeters and the center of curvature is at 10, right? And then the next one here, it's in between right here, right? So this is 3 and number 4 is in between right here, okay? So have a try at these and see if you can prove that other stuff. Good luck.